Now that we've set up our debris sourcing, let's go ahead and set up the debris simulation. So I'll drop in the RBD bullet solver, and under bullet object, turn on emit RBDs, set the same start frame as our previous RBD sim for the main destruction, which was 17, and we want to keep the physics the same in this simulation compared to the other one. So I'm just going to pin my viewport to the debris section here and just jump back to our destruction sim, and we'll take a look at a couple of the settings on the RBD bullet solver here. So the gravity is set to 3 times the default gravity, so we're going to copy that over. And actually, I think that's the only setting that we really want to make sure that we copy from the previous sim. Yeah, for now, just copying that same gravity value will be fine. So let's go back to debris on our RBD bullet solver here. Let's go to forces and set this to 3 times that default gravity. And we can turn the drag on here as well. Copy that gravity and paste the relative reference into the wind velocity. As I mentioned when we set up the primary destruction sim, I like setting this channel reference for the wind velocity to refer to the gravity so that when you start adding drag, it doesn't slow down the rate of fall on these RBD pieces, which I think looks a little bit weird and fake when we're dealing with something heavier like these bits of ground and rock and such. So we've got the physics that we need copied over from the previous sim. We have RBD emission turned on here. So let's connect our debris source to that RBD bullet solver. And with this emit RBDs option turned on here, this is going to add the frame number to the names of all the pieces that are being added to the sim. However, we need to make sure that all the pieces going into the sim on every frame are still unique within that set. So currently, if you look at all of these source debris pieces here, we have almost 2,000 pieces, and we have 612 unique names. So we'll just set some completely new names on these. So I'll drop in an attribute wrangle. This is going to run over points, and we'll set the string attribute name equal to debris underscore, and then add the point number, so I to A, to convert the integer to a string, pass in the point number. I'll rename the wrangle to unique names. You can middle mouse on this and see that we have about 2,000 pieces and the same number of unique names here. And we actually don't need some of this other data that's being copied over as well. The only attribute that we really need from our copy to points here is this velocity. I'll leave this path attribute there, but everything else can really be deleted or turned off in the copy to points here. So for this copy attributes, I'm just going to turn this off entirely. We can turn off the multiplying attributes as well, because we're not really dealing with alpha here. And I'll leave this velocity adding turned on. And then after the copy to points, we can also just delete that variant attribute since we don't need that anymore. So I'll select that under the primitive attributes on an attribute delete SOP and clean up that. So now we have this nice clean input here, and we can now set some properties on this with our RBD configure. So these are going to be active pieces, and I'll set some speed limits on here as well. I'll set a speed max and a spin max to 50 and 20. And you could set the bounce on the bullet solver itself, or you could just override it here. So I'll set the user bounce, set that to a value of 0.05. Just kind of personal preference whether you want to set that in the RBD configure versus on the bullet solver itself. And you can see down at the bottom here, we do have an RBD bullet emit option, but the emission will work just fine if we don't turn that on. So we've set the bounce and the speed limiting, and we have some velocity from our original instancing points, but let's also set some angular velocity on here as well. So I'll drop in an attribute randomize, call this randomize W, set the attribute name to W for our angular velocity. The range will go from -1 to 1 for X, Y, and Z. And let's set the global scale to 10. So now we'll go back to the start frame of the sim here. And let's make sure that we're displaying the current simulation in our timeline. So I'll go to our simulation selector menu down at the bottom here. And let's go to Object Debris RBD Bullet Solver .NET and then display this bullet solver. And then finally, let's flipbook a new frames just to verify that we have this working properly. I'll just flipbook this up through frame 30 to see how it's all looking so far. And the simulation looks a little bit messy at this point, but we can verify that our emission is working properly and we're not seeing any major technical problems or anything. And we can get this to start looking nice by adding in some colliders. And actually, before we add in the collision objects to this sim, I'd like to also point out the collision shapes for the active pieces here. And we didn't really check the collision shapes for our primary RBD sim because everything was working properly. We weren't running into any major problems to debug and things worked pretty well. However, with debris and very small RBDs in general, you do have to be a bit more careful about your collision shapes sometimes. So we can go to the Visualize tab on the RBD Bullet Solver here and turn on this Show Geometry Representation. And this is actually quite slow to display this collision geometry representation. So we could potentially go to a frame with fewer pieces, so this isn't quite as heavy. And if we take a look at these pieces here, you can see that the convex hulls that Bullet is using generally do a pretty good job at approximating all of these shapes. However, some of the smaller ones do tend to get a bit rounded out. So if we select perhaps this one right here, you can see that this collision shape is not quite as successful as the others. Hopefully that's not too hard to see, but some of these other objects are well represented by their collision shapes, but the smaller they are, the more that this default collision padding on this bullet object tab can become an issue. So this collision padding does tend to round out and smooth out these collision shapes a little bit, and this default padding is fine in most cases where you're working with some larger pieces than in a debris sim here, but in this case it can become a bit problematic. So sometimes when I'm working on debris like this, I will turn that collision padding all the way down to 0. And let's reset our simulation. And after resetting that sim with the collision padding turned to 0, now you can see that this collision shape looks perfect. This is exactly what we expect to see even for these tiny pieces like this. So that's definitely something to watch out for when you're simulating very small RBDs like this. So let's go to the Visualize tab and turn that off, because as I mentioned, this is very slow to display, so you probably don't want to leave this visible as you're working. And now let's merge in some collision objects. So let's drop in 3 different object merges. The first one I'll point to Destruction and Collide Creature. Second one I'll point to also Destruction and the Collide Ground. And the third collider here is going to be our previous primary rigid body simulation. So we'll point this to Destruction, and I forgot the name of the null that we used there, so let's jump back to our Destruction setup. And it looks like we actually don't have a null after our transform pieces. We have a null for the render scale Destruction, but let's also add in a null just after the transformed pieces here. And I'll call this simmed destruction. Then go back to the debris setup, and let's point this object merge to that. And then we can merge all of these things together. Now the creature collider and the ground collider should already have some decent attributes set from their previous RBD configure SOPs, but this collision shape for the actual destruction sim that we did previously will need some different attributes. So let's drop in a new RBD configure SOP underneath that one. These pieces were previously set to be active, so now let's turn them off, force those to be inactive. We'll set animated equal to 1, so it picks up the transformations of all of these pieces. Set deforming to 0. And now we should be all set to add these colliders to our debris simulation. So for the previous destruction sim, we merged in our colliders into the first input of this RBD bullet solver. In this case, I'll show you the alternative and merge those colliders in with this collision geometry input here. So we'll connect that collision geometry input to our merged colliders. And then on the bullet solver here, let's go to the solver tab and collisions. And let's turn the bounce way down to 0.05. Then rewind our simulation to the start and display that RBD bullet solver. And then let's once again do another flipbook to see what this looks like with our collider meshes added. And I've flipbooked this up through frame 60, and things are looking quite good. Everything looks like it's working nicely, and this extra debris layer is adding just so much realism and detail and visual richness to this effect, and I'm happy with how this is looking. So we can go ahead and cache out the entire frame range and set up some renders for this. And for my final sim, I believe I turned my drag up a little bit as well. Turned that up to about 0.002. But of course you can play around with that to your liking. And then to set up the caching for these debris pieces, unlike the previous rigid body sim that we did, I'm not going to cache out the transform points. You could cache these out, but it gets a bit more complicated with reinstancing these transform points here because we only have 11 different debris instance pieces, and we have a lot more points here, so we can't use the transform pieces SOP directly. We have to do some extra steps to use a copy to points or something to create enough instances to cover all of these points and then do a transform pieces, and it gets a little bit complicated, which is why I'm just using a packed disk primitive workflow for this instead. So if we display the output of our RBD bullet solver, this is 113 packed disk debris pieces on this frame, and because these packed disk instances just refer to the actual geometry shapes on disk, each of these isn't individually storing that information, we can efficiently cache out all of these directly, since these are essentially only storing the information that they need to do that instancing. Now it is a good idea when we're caching out tons of debris to limit the attributes that we're caching out. So I'll drop in an attribute rename SOP to clean this up a bit. Under the points tab, let's go to the keep attributes, and we want to keep velocity and angular velocity and name, but we don't need any of these other attributes, so I'll get rid of the star next to those. And middle mousing on this attribute rename, you can see those attributes are nicely cleaned up. On the primitive attributes, we don't need to keep any of those. If you had any groups on here, those could also be deleted, but we don't have any, so that's all fine. And now let's drop in a file cache. I'll point this to destruction, make a new debris folder, and call this debris underscore $f3.bgo. We'll let this cache the entire frame range, turn on load from disk, And then we can go ahead and save out this entire sim. And after caching out the full debris simulation, we have something that looks like this. And this is looking very good. I don't see any problems with this, and all of that extra detail is really nice. So let's go ahead and set up the rendering for this. But actually, before we do that, let me just point out why this packed disk workflow works so well for cases like this. And if we go to my caches directory here, and then take a look at the cached out debris simulation here. Currently, our debris simulation is taking up 1.26 gigabytes on disk, which isn't a small amount, but that's not terribly heavy for something with so much detail in it. And all of these individual files, as I mentioned earlier, are just packed disk instances. These don't store the actual geometry on all of these frames. The geometry is stored on the actual instances here. And if you look at the file size of the instances directory, this is actually about the same size as our simulation. So this is 1.3 gigabytes, essentially the same amount of data there. And this is only those 11 pieces of geometry. So perhaps there are a whole bunch of attributes that we could clean up on the actual instance geometry themselves. But that just shows how much optimization we're getting by not caching out all of this geometry on every single frame. And if we take a look at how much debris we have by the end of our simulation, this has over 35,000 pieces of debris. And then going back into our actual cache for the simulation, if we go to the end frames of the sim, even though that's 35,000 pieces of debris, this is actually only about 6 megabytes of data per frame here. So it's highly beneficial to store these as packed disk instances like this. And now let's set up the actual rendering for these. And if you need to do any cleanup before rendering, that's totally fine. Maybe you don't like how some of the pieces are behaving, or some of the debris spills past the collider here and you just want to delete that. You don't need to re-simulate to fix all of those kinds of things. And this is why we made sure to keep this unique name attribute on all of our debris pieces when we cache them out, so that we can easily select these pieces by name. So if we go to selection mode and then points, maybe I'll template our colliders so that we don't actually select those. And then we'll do our selection based on this name point attribute. So you can pick the pieces that you want to remove from the sim and easily clean things up like this. So you definitely want to do as many of these little fixes post-simulation as possible, because it's silly to re-simulate the whole thing when you can make little tweaks like that.